All right. So here it is. So last class we talked about the calculation of the eigenvalues and eigenvectors for this case, the matrix A1. And the matrix A2 is going to be complex eigenvalues and eigenvectors, and you should try to find the solution. The solution of this is at the end of the notes that you have in Canvas, so you can compare. Try to solve it by yourself first, and then you compare. So we're moving into this direction, which is the main part of this chapter 2, which is how we can find a solution for a linear dynamic system using
careful.
transformation. This transformation is going to simplify
Can you give me one of those
our
rice
model.
things?
With that simplification, we can
Give me one of
find
those rice
easy
bubbles.
solution for each of the transform state variables. So that's what we're going to talk today.
If you need to go
Here,
right now, it's fine.
basically, we have in equations that represent the singularity that we found in the space with the eigenvectors and eigenvalues. We're assuming that all these eigenvalues and eigenvectors, they're all different. So if you compare the eigenvectors, we will realize these eigenvectors from 1 to n, they are all linearly independent. We made that definition last time. What did we say about that? When they're linearly independent, what happens? That matrix is formed by each column of this matrix corresponds to one eigenvectors. So if these are all linearly independent, what can we say about Q?
We can take the inverse.
We can take the inverse. We can take the determinant of this Q, and that will be different than 0. The opposite is when some of these columns, which is not the case for this Q, but in any matrix, some of those columns is linearly independent with the rest, and we have a problem, because then it's not invertible, and the determinant for that case will be 0. Right? So in this case, if we put all these eigenvectors in a matrix like this, because they're all different and linearly independent, that matrix will be invertible. Well, let's go back here. We have an equation, singular equation, and what we're going to do, we're going to combine them in a unique equation, matrix equation. These are columns equation. It's a column of n terms, the same thing here, 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 here. But we're going to combine them in a matrix now. So in the first column here, we have this side of the equation. So AQ1 is right here, first column of this matrix. And that column needs to be this equal to the column on this side of the matrix, which is lambda 1 Q1. So we have the first equation in the first column of this matrix equation. The second column is going to be this one here, and this term right there. And we continue in that fashion until we write down the last column, which is AQN on this side, lambda n QN. So we say that we can factorize now this matrix from the left by the matrix A. So if we do that, we take A out of this, and we come up with this multiplication. Now this matrix is nothing else than A times Q, where Q is this matrix we will use to transform the system.
Finishing
the columns of this matrix Q correspond to the eigenvectors and eigenvectors of the matrix A.
Different lecture,
side,
and
we want to have here
only had a few minutes in between period.
One scale by the eigenvalue.
And I was having to
the column 2 scale by the eigenvalue 2, and so on until the last column. These
in between period.
Right by this diagonal matrix.
And I was having to talk to
the eigenvalues. You can verify this, and I suggest you that
someone about very
show that this multiplication will lead actually
urgent
to this result.
and
Try to
important
do it at
matters
once.
period.
Okay? So with that, we have come up by putting all the equations for the eigenvalues and eigenvectors. We put them all together in matrix form. We come up to this nice relationship. What do we have here? we are establishing a unique relationship, a one-to-one
Yeah,
correspondence.
also,
between
comma,
this
it's hard
matrix
for me
A
to
and this matrix capital lambda.
communicate
This capital lambda is very particular because it's a
quickly and
diagonal
discreetly,
matrix
period.
with the diagonal terms being the eigenvalues. And this matrix A is the system matrix of
Like
our
if
system that we're studying.
someone is
Q
talking to
is
me or
invertible.
even
That's what we said before.
near me,
So
comma,
we can multiply this equation from the right and by Q inverse.
it
So we have
interferes with
Q
my
inverse, that
voice
identity.
dictation
So on this
software,
side
so
we'll
I
have
can't
A equal
quickly
to
type
Q,
messages,
capital
period.
lambda Q inverse. So we established there expression for the matrix A. A will be Q lambda Q inverse. The same thing can be done from the left. We multiply by Q inverse. And in that case, Q inverse multiplied by Q will be identity. So on this side, we have capital lambda. And capital lambda will be equal to Q inverse AQ. And
Or
we can
like-
do that because Q is invertible. So by doing that, we come up to these two.
Listening to this lecture right now, comma,
Now,
I'm having
I
to
put
lower the
some
volume on my computer
comments here
because
that you
the
should go
audio
through
can
those
interfere
comments
with
and emphasize the concept
my
we're
dictation
discussing.
to
But
send this
basically
message,
here,
period.
we have a relationship between these two. Question for you. What are the eigenvalues of A? We determine those.
Sorry
Lambda
if
1,
I'm not
lambda
always
2,
quick
all
to
the way to
respond,
lambda
period.
n. What are the eigenvalues of lambda, capital lambda? What do you think?
If
The
I'm not
diagonal
always quick to
matrix.
respond.
Do we know the eigenvalues of lambda?
Just be the same.
The same? Can we show that easily? What would you do?
I have to run through this process again.
So when you have a diagonal matrix, stop sharing. So if we have a diagonal matrix, let's make it simple. You have this one, which is lambda 1, 0, 0, lambda 2. Then to give the eigenvalues of this, we need to solve for this equation, lambda I minus capital lambda. But this is diagonal. So we can obtain this matrix. This matrix is lambda 0, 0, lambda minus capital lambda, which is lambda 1, 0, lambda 2. So we have that subtraction here. So if we subtract these two, we get lambda minus lambda 1, 0, 0, lambda minus lambda 2. And then we need to get the determinant of this. When we do that, we have lambda minus lambda 1 and lambda minus lambda 2 minus 0, and this is equal to 0. So we are trying to find those lambdas that solve this solution. But the solution is already in the standard form. So we know that the eigenvalues for this are lambda 1 and lambda 2. So anytime that you have a diagonal matrix, the eigenvalues are going to be in the diagonal. So
This is a reminder. A to C, F, N.
And that's true for any diagonal matrix.
Any diagonal matrix. So what we're doing with this transformation, actually, we are transforming the system, but we are not messing with the dynamics of the system. The same matrix, the matrix A and lambda are going to have the same eigenvalues, so the dynamics will not be any different. We're going to transform, we're going to have different variables, state variables, but the dynamics is going to remain the same. Okay, so here, what we're going to do to transform our system. What is our initial system? I have it here. x dot equal to ax with this initial condition. We're just trying to solve the zero input response of the system. So that is the initial system we want to transform. And how we're going to do the transformation, we're going to define alternative variable, state variable y. We're going to convert x into y. How? By using this linear transformation. So we're going to transform y through the matrix Q and obtain x. Because Q is invertible, y is Q inverse x. And now we can get the derivative of this. And because this is a constant matrix, the derivative of y is going to be equal to Q inverse derivative of x. For the other expression, the same thing is true. You have x dot equal to Q times y dot. So basically, that's a definition we're making to transform the system, and instead of using x as a state variable, we will use y. We don't know yet why we need to do this, but we will arrive there in a little bit. So this is the system with all the terms that we have, but this is the same system in compact form. This is a matrix equation here. So what we're going to do here to make this conversion, we're going to multiply this equation from the left by Q inverse. So you have Q inverse x dot equal to Q inverse AX. By definition, this term is right here. Q inverse x dot is y dot. So what we have obtained on this side of the equation is nothing else than y dot. On this part, AX or x, you have x here. But by definition, we know that x is equal to qy. So we can replace this expression right here, and we obtain q inverse a qy. So as you can see here, the expression that we have here, q inverse a q, is nothing else than capital lambda. And what we have obtained, because we're using the same set of equations, these are just a scale in a different fashion. This is transformed into new variables. What we have done, we have converted this system in which we can have any matrix A, in which the derivative, for example, look at the first equation here. The derivative of one variable will depend on all the variables in the system if these coefficients are all different than zero. So we have converted the system into that system that is highly coupled into a system in which we have this simple representation. Why this is simple? Who can tell me? We just talked about it.
Because it only has diagonal terms, the rest
Lambda is diagonal. So if lambda is diagonal, what do you get here? And let's go back here again. So if lambda is diagonal, the same system with two variables. You will have here y equal lambda y, but let's assume we have two variables, and here you have y1 dot, y2 dot. These are the two new state variables we have, but this matrix is diagonal. And this is multiplied by y1, y2. So if we take the first equation, what do we get here is y1 dot is equal to lambda 1 multiplied by y1 plus 0 multiplied by y2. So basically, we can eliminate a term, and we observe now that the state variable for y1 depends on y1 itself, nothing else. It doesn't depend on the other variable. The same thing for the second equation. You have y2 is equal to 0 multiplied by y1, and lambda 2 multiplied by y2. So as you can see, this is very powerful because the system now got transformed into two equations that are totally decoupled. These equations just depend on y1. Do we know the solution of this? What did we say before? It's just one variable. What mathematical equation has this property that the derivative of the function is proportional to the function itself, the exponential term? So that's why it's so powerful, this part. Let me go back here. We will share again. We are not finished with this part yet because we need to see what happened here. This is the initial condition, and we need to convert these and obtain initial condition for the transformed system. So in complex form, you have x at t0 is equal to the initial vectors x0. And we do the same procedure. We multiply from the left by q inverse, and this is going to be y. Q inverse x is y at t0. So that's the initial condition for the transformed set of state variable. And on this side, you have q inverse x0, and we obtain finally that that's the condition we need to apply for the transformed system. So in summary, we are using the definition we proposed, x equal to qy, we are converting this system into this. In expanded form, this is the original system. State variables are all coupled. The changes, the derivative of the state variable depend on a combination of the other state variables. But when we transform these, we obtain this decoupled system because this system matrix now is diagonal. So this is what I put in the whiteboard, exactly the same. So if we have n state variables, you will have n decoupled differential equations with a given initial condition that is going to be determined using q inverse x0. So this is the first component of q inverse x0. This is the second component, and so on until the last component of that vector, q inverse x0. We solve each of the equations independently. So we said, well, what is the only mathematical equation that has this property that the derivative of the solution is proportional to the solution? That's the exponential. And not only that, the initial condition of this needs to be y10. So the solution for that equation is nothing else than this. At time t0, the exponential lambda 1 multiplied by 0 is just 1. So the state variable will start at the initial condition. Okay? And the same thing we obtain for the second and the last variable. Now that we have the solution for the system in the transformed system, y1 all the way to yn, we can apply the transformation back to the original system. All we have to do, we need to multiply q by y, and we get the original state vector of the state variable. So we do that, we want to obtain that, we use q and y, and we should get the solution. The terms here, some of them might be 0, but most of the time this is a pretty quite full matrix. And then if we do the multiplication, basically here to get this result, we multiply q11 by y1 plus q21 multiplied by y2 plus all the way to qm1 multiplied by yn. And that's how we get the first row. And that first row will correspond to the solution for the state variable x1. We continue with the second row. We multiply these terms by each one of these, and we get the solution for x2, and so on until the last equation for xn. You can look at this equation, and we can come up with a general solution for this. we can pick arbitrarily any term of this vector. Let's call it y. So the term y for the state variable y, we take the y row of this equation, and we see that that solution corresponds to this. X1 is nothing else than the sum of all these terms. What do we see in those terms? Two aspects. This part is an exponential term that depends on the eigenvalue. So, and the other part has to do with this magnitude of that. This term right here, write it down, is called mode. That describes a mode of dynamic behavior. For example, if lambda is real but negative, how do you think this exponential will be? Exponential decay. What about if this is real but positive? Exponential growth. What about if this is complex? What about if this is purely imaginary, lambda?
Oscillation.
Oscillation.
Decay and oscillation.
If we have a real part with imaginary part, we will have some exponential decay or growth with oscillation. So those are the fourth type of dynamic behavior. We call it mode of dynamic behavior, or for short, we call it mode. So this part here is the mode. And with that, we can anticipate how the system will behave, because this mode will be a part of the solution we will have in each of the state variables. The other part has to do with this. What do you see here? You see something that depends on the system. Where do we get this QKI? Where that can come from? That comes from the system itself. This has to do with the eigenvectors or all the eigenvalues, right? And that depends on the system matrix. And the system matrix depends on whatever interconnection of component and what kind of component you have. So that is a particular characteristic of the system you're studying. But this part here depends on what? This depends on the initial condition you have. Let's say the RLC circuit. You might have some initial energy in the capacitor or the inductor. But if you pick another initial condition, another initial energy stored in those components, then this term will change. This one, it will not change. That depends on the system. This term in the notes, I have one part that talk about this. This has to do with whether this, if this is zero, imagine that you calculate eigenvectors and that particular term is zero. What is the meaning of that? That term for that eigenvalue lambda k, that mode will not appear in the solution of that variable xy. You see? If this is zero, we say that the mode is not observable in that state variable. And that depends on the system. On the other hand, you have this term. If depending on the initial condition, this term now becomes zero, what will happen? The same outcome. This mode will not show up in the solution, but the reason why it doesn't show up is because of the initial condition. We call this the excitation of the mode. If this is zero, we say that the mode has not been excited and it will not show up in the variable. Okay? So those terms are in the notes, and I want you to think about that. In a more compact way, you see here, basically the solution of the state variables in the system is nothing else than a linear combination of the modes. You have modes. What is the solution? A linear combination of those. What is the scalar that will make the linear combination? Alpha, Ki, that depend on the eigenvectors, the term of the eigenvector, and the initial condition. Okay, we did it. Now with this transformation, any system you have, linear dynamic system, let's convert it to this variable y. The system will be diagonal. We can get the solution the solution will be in the form of a mode with an initial condition. And then we convert it back using the matrix Q, and we should get the solution for all the state variables, which is a linear combination of the modes. And this is what I just taught. This is what we're doing. We have the original system. We made the transformation with Q inverse. We have transformed the system into something we can solve because this is decoupled. All the equation for the new state variables are decoupled. We can get the solution for each one of them. And when we get the solution, we convert it back using Q to obtain the solution of the original system. And this is what we're going to do for any linear dynamic system. How are we doing with time? We're doing well. An example, and here we have another electrical system with two components that store energy, one inductor and one capacitor. And you have a resistor R2 and a resistor R1. Because we're interested in the zero input response, we're going to just ignore this and put a short circuit here in the source. And we want to see how the state variables will change in time, starting from an initial condition. Depending on the energy or initial energy stored in this component, we want to see how these variables will change. What are the state variables for the system? The state variables, those are the components. They will store energy.
So the voltage across the capacitor.
Voltage in the capacitor and current in the inductor. So these are the parameters. So you have a high resistance here and also high resistance here. Can you anticipate what would happen here? We don't know yet. We need to solve it, but what do you think?
Well, since the resistors are high, it might damp out quickly, and since the inductor is in parallel with the capacitor, it might behave as a open circuit.
Which
I'm
one?
not sure. Since the capacitor and inductor are in parallel with each other, it might.
But we have this resistor. It will be in parallel if R2 is 0. So what would be the extreme? What happens if R2 is close to 0? What do you think will happen? The capacitor and inductor will be almost in parallel. And what do you expect from that behavior?
Exponential damping.
Exponential damping?
Is
Damping
just
from
RLC parallel. And so current would constantly go, current would go from the inductor into the capacitor and jump back and forth while the resistor, R1 slowly bleeds the whole system.
So these will provide no damping, right? So between these two components, you will have energy going back and forth between the two components. What about this one? What about this R1 is small? What do you think that will happen?
Okay. So R1 is a relatively constant. Okay. R1 bleeds energy from the capacitor, and R2 bleeds energy from the inductor as those energies are transferred. Or no, and the bleeding rate is proportional to how much energy is stored in them at their. So like the more energy is stored, the faster they bleed through. And so when they're discharged, the less bleeding. But like since they're going to be out of sync, it's going to be constant energy draw.
Okay. What will be almost ideal case? R2 should be smaller because that you will have a perfect transfer between the capacitor and the inductor. What about this one? How R1 need to be? Large, because large means almost open circuit. Send that to infinite, it will be open circuit. So basically, you will have a capacitor and inductor in parallel, and if they have an initial condition, they will oscillate forever, right? Without any damping. If we put this, what will happen? Well, you will have a typical RLC circuit. So this is important to a damping to the system. But now we're putting this other resistor as well. That also will take some energy, mainly from the capacitor. So if the capacitor has a high voltage, because the capacitor is gaining energy, this will start dissipating that part of that energy. So if the capacitor gain energy, but some of that energy is being dissipated, then that energy will not be sent completely back to the inductor because we have dissipation here. And when that energy is sent to the inductor, because this will be in the form of current, if you have a large energy going into the inductor, you have a large current, you will have some dissipation here because of that. So these two components will add some damping into the system. Now the question is, would you expect oscillation or not? As a question, we don't know yet. Let's see what we obtain with these parameters. First thing, we need to get the model. And the
Can I ask
model
a
is
question?
obtained from the fundamental equation. So you have Kirchhoff voltage law here, and we have the equation. This is in the first loop, and this is the equation Kirchhoff voltage law in the second loop of the circuit. So let me go back. So this is E, which is 0, because we're going to study the 0 input response. It's going to be E plus the voltage in the resistor R1 plus the voltage VC. And then on this side of the loop, the circuit, you will have VC equal to the voltage drop in the resistor because the current is going in that direction, plus voltage VL. So those are the circuit equations that we have right here. For the voltage in the inductor, that's going to be L, the derivative of the current in time. And for the capacitor, we need, because this circuit has a node in between and you have three currents, then we need a Kirchhoff current law in that node. So you have a current that comes from the left must be equal to the current that goes to the capacitor and the current that goes to the inductor. So this is another fundamental equation from the circuit. So here we can work on this. One thing we can do, we can obtain an expression for the current using this equation. And when we have an expression for the current, we can replace that here. And with that, we can obtain these two set of equations that you see there. We're going to isolate the derivative of the voltage in the capacitor and the derivative of the current in the inductor, and we should be able to obtain these two equations. So by defining the voltage of the capacitor as X1 and the current in the inductor as X2, we can convert this into the state space representation you see here. So this is going to be the A matrix for the system, and this is the vector for the input. We're going to assume that E is 0 anyway, and this is the initial condition for this circuit, which is given right here. You will have a voltage of 1 volt and a current of 1 amp. Okay, so the voltage E have this sinusoidal behavior, cosine of t, but when we review numerical solution of this type of system, we will deal with this part, the whole system actually. But now we're going to focus on the 0 input response. So this term will be 0, and we will just need to study the autonomous system. And that's what we have here. So basically, for this part of the system, you have just one equilibrium point. The equilibrium point is when the derivatives are 0 for x1 and x2. This is 0. So the only way that this is 0 is that x1 and x2 are 0. So x1, x2 equal to 0. That's the equilibrium point for this system. So we want to know how the system will move from the point 1, 1 to the equilibrium point 0, 0. That's what we want to know. To study this problem, then we need to get the eigenvalues of the matrix A. So the eigenvalues and eigenvectors. So in this case, the eigenvalues is lambda 1 is -3 and Q1 is 5, 1. For the sake of time, I want you to check this. It's in the notes, but try to do it by yourself, and then you compare. For the second one is -6, and Q2 is 5. So with the two eigenvectors, we obtain the matrix Q, which is the one we're going to use to make the transformation, which is this one. And with that Q, in the initial condition, we obtain the initial condition for the transformed system, which is this, -1/3 and 4/3. For the two new state variables. With that, as we have determined these terms, these are the initial conditions right there. We multiply this by the mode of each eigenvalue. Exponential of lambda I t minus t0. T0 is 0 in this case. And you have the solution for the variable y1 and y2. And how we obtain the solution for x1 and x2, we get q and multiply by the vector y, which the first term is going to be this one, and this is going to be the second vector of that, second term of that vector. So when you do that, then you get the solution for x1 and x2. So basically, this is the coefficient 1 of the matrix Q multiplied by this, and this is the coefficient, the first row, second column of that matrix Q multiplied by this term. That's the solution. And something similar for X. So in this case, it's straightforward. How the variables will behave, here you have them. Exponential decay. Do you have any oscillation whatsoever? No. Did we know about this before solving this? Yes. Why? Because the eigenvalues were real and negative. So if you have oscillation, it's mandatory that we have an eigenvalue with imaginary part. Okay, that's the first part of the system. If we plot this in time, this is the behavior that you observe. X1 is the voltage. What happened with the voltage in the capacitor? Decrease faster than the current in the inductor. So it seems that we have a very strong discharge from the capacitor, maybe due to the resistor R1, the voltage is dropping. But this voltage doesn't drop all the way to 0, but actually you have a negative voltage that will show up in the capacitor. And that's due to also the behavior of the current. And that's the red curve is the behavior of the current. Both of them, after a little bit, around 2 seconds, let's say, they converge to the equilibrium point, which is 0. Very fast behavior. Another thing we will do most of the time in this type of dynamic study is instead of plotting the state variables with respect to time, we will plot them among them. So here in this axis you have x1 and here you have x2. This is called the phase plane. And you see the behavior of that particular system by looking at what is the trajectory that you will have in the phase plane. In this case, this behavior is typical of a system that has exponential decay.
Quick question, what would an oscillation look like on the phase plane if you just
Spiral. These might look like a spiral, but it is not. So can we get the solution if we start from a different initial condition? We started from 1, 1. Can we start from 0, 1? Yes. We need to replace the value and calculate it and see what we get. And probably we will get another trajectory. What? We need to study that. Can we start from here? From here? Yes, we can do that. And we can try different initial conditions. But before that, let's check a particular initial condition, which is this one, 4 and 2. The voltage in the capacitor is 4 volts, and the current in the inductor is 2 amps. Would that make any difference in the solution? Let's check. So we get the initial condition for y in this case is 0 and 2. What do we anticipate when we see this? This is 0. So what happened with the excitation of the first mode? The first mode is not excited at all. And that's what we see in the solution. The solution is just formed by the second mode of the system. Why? Because we started the system from that point. This point does not excite the first mode. If you get the solution, you plot the solution, what do you see? Exponential decay, both of them. Voltage and current never become negative. They go from the initial value and converge exponentially to 0. If you plot that in the phase plane, what do you see? Straight line. Is that strange? What is that straight line?
Just the balancing of the inductance and capacitance, well, the inductance, capacitance, and resistance of all the elements.
It's very interesting to see this straight line in the phase plane. That's very odd. And what we're going to observe here that actually if we plot here the eigenvectors, this is one of the eigenvectors. Which one? Let's go and check. You have 2, 1, and the other is 5, 1. Which is that eigenvector? This one. What is the initial condition? 4 and 2. So the initial condition is in the direction of the eigenvectors. What did we do by just starting from there? We ignore the other mode. We are just in these areas or area of that space, just that involve that mode. So we started from the same direction of the eigenvector, and we only excited the second mode. This is not excited at all. But if we move away from this, and we are in a point between these two vectors, then we will excite both of them. What happens if we are here? The voltage is negative 2.5 and the current is negative 0.5. We will be in the direction of that eigenvector. What will happen? We will just excite that mode, not this one. And that's what we have right here. That's one case. This is the other case. We start from a different initial condition, but this is in the direction of the eigenvector of the first mode. What is the solution? Exponential decay again. These never become positive, the voltage and the current. They converge to 0. We plot that in the phase plane, and we call this a straight line. So if we are in an initial condition that is not along these eigenvectors, we will excite both of them. Of course, if we are closer to one eigenvector, we will excite that mode more than the other mode, depending on how close we are. We can have a collection of all the system trajectories starting from different points, and we should get something like this. When we have this collection of the solution from different initial points, initial values, we call this a phase portrait. It's a collection of all the solutions. And by looking at this, what do you see? There is no oscillations. Why there is no oscillation? The space is divided here in 4 regions. This one from here to here, from Q2 to Q1, this one here, and this one from Q2 to Q1 again, 4 regions. If you start here, the trajectory never leaves this region. It's there. There is no oscillation. The same thing here, here, and here. This, when we look at the phase portrait, we will recognize this behavior, and we will say this is a stable node. Okay. Why node? Well, there is an exponential decay in any direction. There is no oscillation. Is this stable? Yes, because no matter where you start, the system converges to the equilibrium point. Can we have the opposite? An stable node. Yeah, we can have that. And no matter where you start, you will be pushed to infinity in a given direction. And that's what we have there. We have a system here. We have a system with this matrix. We can calculate eigenvalues and eigenvectors, and you will get this. The eigenvector is not here, but is in the node, I believe. But you see the eigenvalues are real and positive, so the system will have an exponential growth. So no matter where you start here, where do you go? Infinity, going in that direction. This is also a node because there are no oscillation here whatsoever. You have the space that is going to be divided by the two eigenvectors. Can you observe where is an eigenvector here? I can see one somewhere right here, right? So that's an eigenvector. If you are along that eigenvector, you start in that line, you will be pushed through that eigenvector to infinity. That's another behavior. Another behavior, both real, but one is positive and the other is negative, is matrix. We get the eigenvalues, these are the values. One is positive, real, the other negative, real. The negative that is real is stable. So there is an area in the space that the system will try to converge to the equilibrium point. But very soon you will find another force that will push you to infinity due to the other eigenvalue. That's what we observe there. Where should be the eigenvector of lambda 2? Can you see it? You have an eigenvector right here and another right here. This one right here is the eigenvector of lambda 2. Why? Because you start there, it's kind of taking you to the equilibrium point, right? This one is the eigenvector of the other eigenvalue. You start there, it takes you to infinity. So this system, because you have some forces that take you to the equilibrium point and some forces that push you away, it's called a subtle node. Okay? This is unstable, of course. You have a system with subtle node, the system will be unstable. Let's trick the system. We talk about this. And we do it, yes. Imagine you're in the lab. You're not going to start like playing and changing things. You're going to think first and try to anticipate what you're going to get. And what we're going to do, reduce this to 3. What will happen? We were just talking about this. So if you have less resistor, what will happen there? Less dissipation here. So the energy that the inductor will get when receive energy from the capacitor will not be lost importantly. So there will be a lot of energy in the inductor that is going to be sent back to the capacitor. And then the capacitor will do the same thing and send the energy back. But in each cycle here, the dissipation will be less because we're reducing the resistance. What we're going to expect now? Maybe now we're going to have some oscillation. Exchange of energy between one component and the other. Bottom line, yes, we will have oscillation. First thing we do, we calculate again the matrix. This is the matrix now. We get the eigenvalues, and what do you get? Complex eigenvalues. Yes, now we do have oscillation because of this. Are these oscillations going to be stable? Yes or no? We look at the real part. The real part is negative. So you will have exponential decay. That will add stability to the system. But there will be another component that will be related with the oscillation. Here, you already have a matrix in which you have complex eigenvalues. We need to get the complex eigenvectors for this. And this is the procedure. That's the singularity for that eigenvalue. We'll try to get Q1. But because lambda 1 is complex, Q1 will be complex as well. So we have 4 unknowns to determine. So when we do this, because this is a singularity, you will have 2 complex equations, but one of them will be linearly dependent, right? We just pick one. If you separate this in real and imaginary part, for each equation, you will get 2 more equations. So in total, you have 4 equations. But because of the singularity, 2 of these will be linearly dependent. We just pick 2 equations to determine these 4 variables. There is no way you can determine those. So you need to pick 2 variables independently. Just assign any value you want. When you get those, you determine the other 2. What I did here, I solved for A. So I said A is C minus 3B, and B is 3C plus D. That's what we have there. So I can pick here a value for C and D, and I can get the rest. How much is C? It's 1. How much is D? 0. You see? Is there C plus JD? D is 0. How much is C? 1. So you replace those and you get how much should be A, how much should be B. So that's the eigenvectors. How much is Q2? Well, lambda 2 is the conjugate of lambda 1. So Q2 will be the conjugate of Q1. Okay, we're done here. We're going to take it from here, but the solution here is going to be straightforward. We're not going to make any distinction because this is complex. We will apply the procedure in the same fashion as we did it before, and we will get a solution. Yeah. So on Monday, let's not forget, we have a quiz. There will be a quiz of the subject we discussed this week. Okay. I will see you on Monday. Thank you.